All right, so in my second talk, I want to talk about Kahler-Einstein metrics on so-called Fano manifolds. And so fortunately, we have already seen the term Kahler-Einstein metrics in the morning, but that discussion was on domains in Cn, whereas this discussion will almost completely be on compact manifolds. Okay, so at the very beginning, let me again, yesterday I talked a bit about Kähler metrics and gave you some background. So let me maybe repeat myself a bit. So let me again give you a very quick introduction to what Kähler metrics are. So M omega is called Kähler. So again, M is always going to be a complex n-dimensional compact manifold, and omega is going to be a special form. So that's the additional data which we are going to, define the Kähler condition using omega. So it's called Kähler if omega is a two form such that locally we have this very nice system of coordinates. So whenever I say coordinates, I generally mean holomorphic coordinates, such that locally omega can be written as this. Right, so again, this is very similar to what we saw in the morning, such that these Gij bars, this is a local matrix of functions, and we wanted to satisfy the following two conditions. So Gij bar is Hermitian symmetric and positive definite. And I also want this form to be closed, and in terms of these coordinates, there is an equivalent, this is equivalent to the statement that Gij is delta Ij plus. Okay, so the statement is that if d omega is 0, then one can find such a convenient set of coordinates so that the first order term in the Taylor expansion vanishes. Okay? And then we saw that if omega is such a form, then omega corresponds to a Riemannian metric, okay, which can be written as d squared as Gij dxi dxj, where these xi's are basically the real and imaginary parts of my holomorphic coordinates. So for instance, I could write this as this, okay? And then, Gij is basically this matrix given by the real part minus imaginary part, right, where this is the matrix Gij bar, okay? So then we also had defined a notion of Ricci curvature, which again you saw a definition again today morning. So it's defined to be this form minus square root of minus 1 d bar log of determinant of Gij bar. Okay, so one thing to notice about this is that if you take d of Ricci omega, you get 0. Okay, that's because d is d plus d bar, and then of course when you apply that here, you get 0. So which also means that, so if you've seen a bit of de Rham cohomology, that's basically, de Rham cohomology groups are defined by taking the closed forms and modding out by the exact forms. So in particular, this form represents a cohomology class in the second de Rham cohomology, right? Just because the exterior derivative applied to that is 0. Okay? So it turns out that this is actually a very special kind of a class. So a priori, you might think that this class depends on my choice of the metric omega. But it turns out this class is actually independent of the choice of omega. And it's called the first Churn class of M. So let me maybe say a few words about that. Okay, so it's denoted by C1 of M. So the point here is that Gij bar defines a Hermitian metric on the holomorphic tangent bundle of M. So if you remember, the holomorphic tangent bundle is locally simply spanned by these guys. Okay, so it's spanned by all the unbarred tangent vectors. Okay, and what is the metric that it defines? Well, let's say you have two elements here. Then in order to find the inner product, you just define this to be Gij bar psi I eta j whole bar, where psi I is the component of psi in the del by del Zi direction. Okay, so that defines a Hermitian metric on the holomorphic tangent bundle. So this implies that if you take the determinant, this actually defines a Hermitian metric on the determinant bundle of this. So this defines a metric on what is denoted by as Km inverse. So by definition, this is the nth wedge product of the 1,0 tangent space. Or in other words, it's locally spanned by this single element. Okay, so clearly, I mean, this is going to be a rank n holomorphic bundle. Similarly, this is going to be a rank 1 holomorphic bundle, which means it's a complex or a holomorphic line bundle, and this is called the anti-canonical bundle. Okay, so the minus 1 basically indicates if you don't have that minus 1, Km is basically called the canonical bundle, and that's spanned by the duals of these guys. So it's spanned by this, right? And this plays an important role in algebraic geometry. So the dual of this is called the anti-canonical line bundle, and the determinant of that matrix gives you a Hermitian metric on this bundle. But remember, if H is a Hermitian metric on a line bundle L, then if you take minus square root of minus 1 d bar log of H, which is basically square root of minus 1 times the curvature of this Hermitian line bundle, that's a representative in the first Churn class of L. Okay, and now we have a similar formula for the Ricci curvature, where instead of H, you have this particular Hermitian metric. Okay, so the upshot is that no matter what Kähler form you choose, the Ricci curvature is a representative of, I mean, this 2 pi is an annoying factor which I might sometimes ignore, but it's basically 2 pi times the first Churn class of the anti-canonical line bundle. And this depends only on the holomorphic structure on M. Okay, this does not depend on omega. And we define this to be the first Churn class of M. So whenever I say first Churn class of M, I basically mean this guy, right? Or maybe 2 pi times. Okay. All right, so that's as far as background in Kähler geometry is concerned. So next I want to again introduce Kahler-Einstein metrics. Okay, so before I do that, let's talk a bit about the uniformization theorem, because I guess most of you would be aware of what the uniformization theorem is. So the idea is, suppose I take let's say a compact oriented surface. So then these are all classified. They're basically just either a sphere or a donut or some connected sums of these tori, right? So so it turns out that, this has Euler characteristic 1, this has Euler characteristic 0, and this is Euler characteristic negative. Okay, so then what does the uniformization theorem tell us? So this implies, given any, so for all metrics G naught, so these are there exists a metric which can be written as some scaling factor times G naught, but this scaling is of course by a function, not by a constant necessarily. So if you vary u, you'll basically get a whole family of metrics, and that family is denoted by bracket G naught. So that basically is the conformal class of G naught. Why conformal? Because for any metric in this class, the angles are basically the same, right? Because all you're doing is you're scaling the distance, but the angles between tangent vectors remain the same. That's why all metrics here are said to belong to the conformal class of G naught. So then the uniformization theorem says that there exists a G in this conformal class such that if you look at the Gauss curvature, that's going to be a constant, and you can take that constant to be the sign of the Euler characteristic. Okay, so this is the Gauss curvature. So in general, if the Gauss curvature is constant, the sign of that constant has to be the sign of the Euler characteristic, and this follows from, of course, the Gauss-Bonnet theorem, right? But this actually, uniformization tells you that there exists such a metric so that the Gauss curvature can be made constant. Okay, so how does this relate to Kähler geometry? Well, if you take the conformal class of G naught, this actually makes sigma into a Riemann surface. So this conformal class actually determines a complex structure on sigma, and this correspondence is via what are called as isothermal coordinates. So you can choose a special set of coordinates so that locally G naught can be written as h times dx squared plus dy squared. Okay, and then z equals x plus square root of minus 1 y becomes a holomorphic coordinate on that local patch, and then you can check that if you sort of vary your local patch, the corresponding transition functions will be holomorphic, right? So this actually defines a complex structure. So this is holomorphic. And then if you look at the area element of G naught, that gives you a two form. So this is by definition just h times dx wedge dy, and clearly it's a Riemann surface, so the dimension is 2. If you have a two form, if you apply exterior derivative to it, there's no other place to go, right? So the exterior derivative of any two form has to be 0, right? So clearly, since the complex dimension of sigma is 1, this implies that d omega is 0. So this now gives you a Kähler form on your Riemann surface. And so if you compute the Ricci curvature of this omega, so maybe I'll call this omega naught. So if you compute the Ricci curvature of this omega naught up to some constant, this will turn out to be the Gauss curvature times the area element. Okay? So you can go and check maybe the wiki article on how to calculate the Gauss curvature, and you will see that the formula is exactly d bar of log of h, essentially, up to a constant. Okay, so this means if you find a metric whose Gauss curvature is constant, this is equivalent to the statement that the Ricci curvature of the corresponding omega is basically this constant number times omega. So the uniformization theorem is equivalent to the statement that there is a Kähler form omega whose Ricci is a multiple of omega, and you have seen already in the morning lecture that this is the Einstein equation, right? So, Kähler-Einstein metrics are a natural generalization of something that's quite classical, namely the uniformization theorem. Okay, so now I'll just formally give a definition of Kähler-Einstein. So omega is called Ke if Ricci of omega is some multiple times omega, where lambda could be any real number. Okay, so standard example is, so I guess you can look at the projective space. So this is basically the set of all lines in Cn plus 1, so modded out by C star. Okay, and then you define the Fubini, so-called Fubini's 2D metric. So let me see if I remember this. So it's d bar log mod psi squared, where you basically, where psi is psi naught, etc. up to psi n, and you represent points in Pn as equivalence classes of these guys. So they are so-called homogeneous coordinates on Pn, right? So it turns out if you take the Ricci curvature of this, it's a nice elementary calculation in linear algebra that this will turn out to be, so maybe I should have a, so it's some constant, I think it should be n plus 1 times omega fs. Okay, so in any case, it's some positive multiple of omega, of the Fubini's 2D metric itself. A second example was basically discussed in today's morning lecture. You take the ball and basically take the Bergman metric. Okay, so this is going to have Ricci, some negative constant, so you can normalize so that negative constant is 1, and it's going to, the Ricci of this is going to be just minus omega b. So this is an example of a Kähler-Einstein metric with negative Ricci curvature. Of course, this is, the difference here is that this is a compact example, this is a non-compact example, but you can always take quotients by groups, right? So for instance, in the two-dimensional, or in the complex one dimension, these are all essentially quotients of the disk, right? With the hyperbolic metric. Right, so now a natural question is, when does a Kähler manifold admit a KE? So of course, a given Kähler manifold will have plenty of Kähler metrics. So the question is, when does it actually admit one of these special kinds of Kähler metrics? Okay, so right at the outset, there is one sort of obvious topological restriction. Okay, to describe that, I need one more definition. So I say that a class alpha, so let's say this is a cohomology class in the second de Rham cohomology group. We say alpha is positive if alpha contains a Kähler metric. Okay, so recall that if omega is scalar, then d omega was 0. So omega is a closed form, and that was the definition of being Kähler. So that means omega should also represent a cohomology class. So that means omega represents a cohomology class in the de Rham cohomology group. Okay, so then we say that an arbitrary element here is positive if it actually contains such a Kähler form, right? Okay, so then if you look at the Einstein equation, so yeah, if you look at this, the class that is represented by omega by definition is a positive class, right? I mean, that's how I've defined positivity of Kähler, of cohomology classes. So then, depending on what the sign of lambda is, I mean, on the left-hand side, you have something that represents the first Churn class of your manifold, right? So depending on the sign of lambda, your sign of the first Churn class is decided. So if you have a Kähler-Einstein metric, your first Churn class must have a sign. Okay, so this implies that if omega is a Kähler-Einstein metric, then the first Churn class splits into 3 cases. So either it's positive if lambda is positive, it's 0 if lambda is 0, and it's negative if lambda is negative. Right? So clearly your first Churn class must have a sign, and of course you can ask whether this is an actual restriction or does the first Churn class always have a sign? Well, it doesn't, because if you take, for instance, let's say P1 cross a Riemann surface of high genus, then the first Churn class of this does not have a sign. Right? So this is a genuine obstruction to there being Kähler-Einstein metrics. There's also a little observation on rescaling. So suppose lambda is not 0 and Ricci omega is lambda omega. Okay, so then you just consider the following. You scale your omega, so consider omega tilde as absolute value of lambda times omega. This is again going to be a Kähler metric because you're multiplying by, you're scaling by some positive factor. If you calculate the Ricci, because the Ricci has a log, so multiplying by a scalar, once you take d bar, that's anyway going to be killed. So the Ricci is going to be the same as earlier. But then we are assuming this is Einstein, so you have this. But then omega is given by omega tilde divided by this. So this is the sine of lambda times omega tilde. So the moral of the story is that by rescaling, one can always assume that our Einstein metric has that Einstein constant is either plus minus 1 or 0. So without loss of generality, can assume that lambda is either 0 or plus minus 1, right? Okay, so now let me summarize what is known. So this is due to yaw when lambda is 0 and due independently to yaw and oba when lambda is negative. Okay, so the theorem says that if the first Churn class has a sign and it's non-positive, then this implies that there exists a KE. Okay, so that means that the sign of the Churn class is the only restriction that is there. Okay, but I have of course left out the case when lambda is positive. So when lambda is positive, there are actually obstructions. So the first obstruction I believe was found by Matsushima. And then there's a more analytic obstruction which will play a role in today's talk, which is due to Futaki and its sort of generalization by Tian and Donaldson. Okay, so in the positive Churn class, this is mainly due to Tian. Okay. All right, so this is sort of this discrepancy between, or this trichotomy that lambda is 0 or plus minus 1 is basically similar to this, uniformization theorem where you have to have special, you have to deal with the Euler characteristic being positive, 0 or negative. And purely as a PD, it turns out that if you want to prove the uniformization theorem, it's the hardest for the sphere from a PD point of view. But of course, if you know a bit of complex analysis or Riemann rock, you know that for sphere it almost becomes a triviality, right? So, but from a PD point of view, it's hard, and that's sort of the same reason why that problem is hard is essentially the same reason why this problem is extremely hard but of course I must say that as a PD problem that the Riemann surface case was solved much earlier. For instance, there are Ricci flow proofs of the uniformization theorem on S2 and so on. So that problem is still much easier than this. But so for anyone who has some experience with PD, this is sort of a recurring, even if one deals with the Imabe problem, there is always an easier sign to work with and there's a hard sign. So the positive case is usually hard because maximum principal techniques fail. So if you have some experience with PD, you'll know this. Right, so then the definitive result here was actually quite a recent result. It's due to Chen-Donaldson-Sun in 2012, I believe, and also due to Tian, especially in dimension 2. And that is where he, I guess in dimension 2, Futaki's invariant is enough, but for higher dimensions, Tian had to find a refined obstruction. And it turns out that if M is Fano, so this just means that the first Churn class is positive, then M admits a KE if and only if M is what is called as case stable. Okay, so it was already a conjecture of Yao in the 80s that existence of a Kahler-Einstein metric should be related to some form of stability. And the exact notion of stability was discovered by Tian in 97. Okay, so let me maybe make a few remarks. So the general principle in complex geometry is that the existence of these special kinds of metrics or connections or any special kind of differential geometric object should be related to some form of stability. And the important point is that the stability is usually a very algebrogeometric quantity, which means that at least in principle one can check this criteria, whereas this is usually, I mean, just given a Kähler manifold, it's usually hard to know when it admits such special metrics. And of course, they're sort of connected by trying to solve a nonlinear PDE, right? So the first instance of this, as far as I know, is the Narasimhan-Seshadri. Right, so I'll explain that. I think that will take up the rest of the talk, right? So I don't want to go into a lot of technical details, but I just want to give you a heuristic picture of what case stability is. So the first example of this sort of principle was the Narasimhan-Seshadri theorem on flat connections on Riemann surfaces, which was of course later extended by Donaldson, Uhlenbeck and Yao. And there are actually plenty of examples of this phenomenon happening again and again. So maybe I should make a couple of other remarks that, as I said, case stability was defined by Tian in his 97 paper, and he in fact proved this direction of the implication. So he showed that if M admits a KE, then a necessary condition is that M is case stable, right? So he proved this implication when the automorphism group was empty, and in fact this helped him construct examples of M's with dimension M as 3 such that the automorphism group of M is empty. Pardon? Yeah, sorry. So trivial, right? Yeah, thanks. Right, and of course not zero. But yeah, automorphism group is identity. So he constructed examples of such Fano three-folds which do not admit any KE. Okay, so this was sort of I mean, both the obstructions of Futaki and Matsushima involve the automorphism group of M, and they basically are vacuous if the automorphism group is identity. Okay, so as I said, in dimension 2, Tian showed that these obstructions are the only obstructions to existence of KE. Okay, but so then a question was that, I mean, okay, so you assume that the automorphism group is trivial, then does that Fano manifold admit a KE? And his examples showed that even that conjecture is not correct. Okay, so one actually needs this refined notion of case stability. Right. Okay, and maybe I should make a final remark here that this implication in general for possibly non-trivial automorphism groups, So again, when I say automorphism, I strictly mean the identity component of the automorphism group. So of course, you're allowed to have discrete automorphism group. So, so the identity component, in general, if the identity component of this is not trivial, this was done by Robert Berman. Okay, so one direction, the, so to speak, easy direction, which is actually not very easy at all, was already done before Chen-Donaldson-Sun. But so their main theorem is the reverse implication that this is in fact sufficient. Okay, so let me now spend the rest of the time talking about case stability. And maybe I also want to sort of connect all of this to yesterday's talk about projective embeddings, why these uniform projective embeddings are a good thing for this problem. Right, so before I define case stability, here's just a heuristic picture. So let's say I have a function which is defined on some finite dimensional space as a real valued function, and let's say this is convex, and I'm trying to minimize this. So I'm trying to find a minimum of this functional. Okay, so there are essentially three pictures. So you could either get lucky and the graph of f looks like this, in which case you do have a minimum, or you can have something like exponential decay, or you have something that sort of goes off to minus infinity, right? So this picture is called stable, this is called semi-stable, and this is the unstable picture. So in the stable picture, you do have a minimum, okay? In the semi-stable picture, you basically have a minimum at infinity, right? And in the unstable picture, your function is not even bounded below, right? So there's no hope of getting a minimum. So the way to sort of characterize these guys is to basically look at the slope. I mean, one way to characterize is to look at the slope at infinity. So if you notice, the slope at infinity here is positive. Here, the slope at infinity is 0, and here it's negative. Okay, so in other words, if I sort of take a ray going off to infinity, if I restrict my function to that and compute the derivative at infinity, I'll get something that's positive here, 0 here, and negative here, right? So these three, sort of an infinite dimensional analog of this will be k stable, k semi-stable, and k unstable. Okay, so just keep this heuristic picture in mind. So in order to define case stability, one actually doesn't just take, so I mean, it's possible to define a sort of functional on all possible Kähler metrics on a manifold and then carry out this process where instead of straight lines, you define what are called as geodesics in the space of Kähler metrics, and then basically you have an exactly analogous picture. But what Tian did is, instead of sort of taking a geodesic in the space of Kähler metrics, you allow the manifold itself to vary. Okay, so instead of right, so what I mean is the following: you embed your manifold in some big projective space, and you allow your manifold to degenerate. Okay, along the one parameter family. So that one parameter family is basically going to be parameterized by a torus, C star. So you have this one parameter family and you look at what happens as t goes to 0. So in the limit, you might have a very sort of singular variety. So this limit is just an algebrogeometric limit. and then you compute a certain quantity on this limiting variety. That will be the analog of the slope at infinity. And if that is positive, you say that your manifold is stable. If it's negative, you say that it's unstable. Okay? So is the picture clear? So let me maybe give you the formal definition. It's a bit technical, but I'll give you basically the sort of canonical example that you can work out in this situation. So let me give a definition. So a special degeneration of M. So now all my manifolds are always Fano. So a special degeneration of M consists of two things. So firstly, it consists of an embedding into some big projective space via sections of the anticanonical bundle, but because it's Fano, the anticanonical bundle is positive, but then by Kodaira we have seen that one might have to raise it to a large enough power in order to have enough sections for there to be an embedding, right? So, so this R is called the exponent of the special degeneration. And secondly, we want a C star subgroup of the group of the automorphism group of this Pn. Right, so the automorphism group is of course PGL, and we want a C star subgroup of that. Okay. So then we, if we take the limit, the algebrogeometric limit as, so you apply lambda t to M, so that sort of moves your family of, it moves your Fano manifold. You take the limit as t goes to 0. You want this to be a normal variety. So in general, it could be really bad. So in fact, the example I'm going to give is not a special degeneration because this W will turn out to be pretty bad, pretty singular. So it's okay if you don't know what a normal variety is. From an analyst point of view, what is important is that normal varieties are complex manifolds outside of codimension 4 or complex codimension 2 sets. Okay, so that's good when you want to do analysis because cutoff functions, etc., behave very well if your singular set is very thin, right? So, so maybe before I tell you what is case stability, let me just give you an example of this. So one can think of P1 sitting inside P2. So choose homogeneous coordinates on P1 and map that to this. Okay, so it in fact turns out that in this case, this is actually an embedding via the sections of the anticanonical bundle of P1. And so if you use coordinates x, y, z, then of course P1 is basically the image of y squared minus xz is 0. Right? So if you look at the equation satisfied by these quantities, that's just y squared minus xz is 0. So then one can take the following torus action. Oh yeah. Xi1, right? Yeah, thanks. Okay, so I take the following torus action. Okay, and see how it moves my P1, right? So if you, so what is the equation satisfied by the manifold at the tth stage So if you put mt is lambda t times my p1, then it's easy to check. So I mean, if the action on this is given by this, to find out what equation is satisfied, you have to take the dual action. So it's going to be this, right? But since you're working in a projective space, this is the same as t cube minus xz is 0, right? Just multiply everything by t. Okay, now when you take t goes to 0, you take the obvious limit. This converges to the equation xz is 0. So when I say algebrogeometric limits, I mean sort of the most obvious thing to do, right? So, and of course this is very singular, it's the union of two lines. Right, so in particular this is sort of, I should have said a non-example because this guy is not a normal variety. And a quick way to see this is I just said that the codimension of the singular set has to be at least 2, right? But here, I mean the dimension itself is 1. So if it's normal, it cannot be singular. But this is singular, so it's not normal. Okay, so this is not a special degeneration because what you get in the limit is not a normal variety. But it's sort of the simplest example to write down as to sort of what kind of limits you take, right? Okay, so then in order to define K-stability, I have to basically tell you what this sort of slope at infinity is, right? And then depending on the sign of that, I can define stability. Okay, so now given a special degeneration lambda, one can associate a number. So before I tell you what that number is, notice that W is a fixed point for the action of this torus, right? Because it's what you get when you pass the limit. So clearly the torus cannot further move your limiting variety, right? So before I define what that number is, note that C star keeps W fixed. So suppose lambda is generated by a holomorphic vector field, little w on Pn, right? So this little w is basically just the derivative of this one parameter family at t equals 1, right? So I'm assuming that this lambda is generated by such a holomorphic vector field. Then w will be tangent to capital W, right? Because the C star action keeps your capital W fixed, so this tangent vector better not move out of capital W, right? Okay, then I need another notation. This theta W be the Hamiltonian of this holomorphic vector field W. So that means that this holomorphic vector field is basically just given by the gradient of theta W. So essentially when you move by lambda, you're essentially moving along the gradient flow of this function theta W, right? So on Pn, you can always find such a, given a holomorphic vector field, you can always find such a Hamiltonian, okay? So then we define this number, which is called the Futaki invariant of M, and this degeneration is defined by a certain integral. So it's again, for the rest of the talk, it's unimportant what these quantities are. Just for completion, I want to give you the formula. This is given by something of this sort. Okay, so you essentially compute a certain integral on this limiting manifold or limiting algebraic variety. Okay, so and in fact there is an algebraic formula due to Donaldson. So in fact, for the analytic formula, it's important that W is a nice variety. So in particular for normal varieties, Tian and his collaborators had already defined this Futaki invariant. But it turns out that W could be very even more general kinds of varieties. And using Riemann rock, Donaldson was actually able to give a definition of the Futaki invariant too. So presumably, I mean, at least in principle, one doesn't need this word special in order to define K-stability. But in the end, all you need to check are special degenerations. So it's enough to actually just look at these special kinds of degenerations. Okay? Right, so then the definition is M is called K semi-stable if for all degenerations this is non-negative. Okay? So of course, remember degenerations also mean that I get to pick the embedding into a large projective space, right? So you can imagine that this is actually extremely hard to check because you need to, in principle, check for all possible degenerations, right? So all possible embeddings, all possible C star families, and then compute these numbers. And then M is called K stable if in addition this being equal to 0 is equivalent to the statement that W is isomorphic to M. Okay, so for some G in the automorphism group of the projective space. So that means in so you should think of it like this. You have sort of the PGL orbit of M, and W might potentially lie on the boundary, but if the Futaki invariant is 0, then if your manifold is K stable, it forces W to lie in the interior of the orbit, right? Okay, so just because I mentioned this example, one can actually check that the Futaki invariant for this guy is something like 3/4, which is positive. And how do you do this calculation? You of course don't use the analytic formula, but you use the algebraic formula due to Donaldson. So you can pick up any sort of reference for extremal metrics, and you will find an algebraic formula, and you can calculate that this is 3/4. It's positive, which is good because P1 has the Fubini-Studi metric, which is Kahler-Einstein, right? So of course, if something has a Kahler-Einstein metric, the Futaki invariant for all degenerations better be positive. Okay, so I guess I have around 5 minutes left. So maybe let me sort of give you a very quick outline of the proof. Okay, so the outline, I mean, since the appearance of Chen-Donaldson-Sun's paper, there have been 3 other proofs of this theorem. So the outline of the proof that I'll give is joint work with Gabor Szekelyhidi. And of course, this is using techniques developed by Chen-Donaldson-Sun on the way to their proof. So the idea is that, so whenever you have a PD that you want to solve, there is one sort of standard method is to set up some sort of evolution. So find this family of metrics omega t, which connect a certain metric omega naught to the metric that you actually want, to a Kahler-Einstein metric. So the way that Chen-Donaldson-Sun do this is, so in CDS, they basically use a sort of continuity method with Kohn angles. So it's something of this sort. Where this is the current of integration along some divisor, and then you should think of these metrics as basically Einstein metrics. So away from this this divisor, these will basically just be regular Einstein metrics, and they have sort of Kohn singularities along a codimension 1 set, right? And then the idea is you just vary the Kohn angle. So this will have Kohn angle 2 pi beta. So as you vary beta towards 1, your conical metrics will become smooth in the limit, and hopefully in the limit you get something that's smooth and Kahler-Einstein. So the method that we use is via what is called as a smooth continuity method, which means we fix a reference Kahler metric in the first Churn class of M. So alpha is positive. And we try to solve the following equation. Okay, so you let I be the set of all times for which there is a solution. Okay, I'll call this star t. Then what is our goal? Our goal is to show that 1 belongs to I, right? Because if 1 belongs to I, that means you have a solution at t equals 1, so that this term disappears and you get Ricci of omega 1 is omega 1, right? So that would be a Kahler-Einstein metric. So our goal is to show 1 belongs to I, and there are essentially 3 steps in all of this. So the first step is to show that 0 belongs to I. So if you put t equals 0, this term disappears. So you are essentially solving a prescribed Ricci curvature equation. You are given an alpha, and you want to find an omega so that Ricci of omega is alpha, right? So that's a prescribed Ricci curvature equation, and this was done by Yao in his solution to the Calabi conjecture. The second step is to show that I is open. This is generally a standard thing using a certain implicit function theorem. And the third step is to show that I is closed. Okay, and this is where case stability comes into the picture. So maybe in just, I have like 17 seconds, but maybe I'll take 1 extra minute. So essentially what happens is that, how do you show something is closed? So yeah, by the way, once you show this is closed, then of course the interval 0 to 1 is connected, and so it must be the entire interval, right? So that means 1 must belong to it. Right, so how do you show, so maybe just 1 more minute. So to show something is closed, you take a sequence tk converging to some capital T. So then you want to basically show, so goal is to show that capital T belongs to I, right? So the idea is you take this sequence of metrics Okay. By this general theorem of Gromov, in Gromov-Hausdorff topology, they converge to some compact metric space. And then by extending the argument that I presented yesterday, so this extension was done by Gabor in his earlier paper. So of course, this used techniques from Donaldson-Sun and Chen-Donaldson-Sun. One can show that this is actually homeomorphic to a normal projective variety. So now we get something that, so we get a whole family of Kähler manifolds that converge to something that's a normal projective variety. Okay, so if you can embed this entire picture in this PN, you have your first embedding, and then they're converging to this normal projective variety. Right, so then the idea is that this gives you a candidate to test K-stability. So if you know that your manifold is K-stable, then one can show, especially if T is less than 1, one can show that W has to be biholomorphic to M. And in fact, because of this metric convergence, one can actually get a limiting equation. So it turns out that W has a metric omega t which satisfies an equation of this type, where beta is some sort of limit of this form alpha that we have. Okay, so then K-stability will imply that W has to be biholomorphic to M. So that means M also has to have a metric omega t which satisfies such an equation. So we have a solution at time t. Right, and then at t equals 1, the argument is slightly different. Okay, so that's how one uses these projective embeddings and K-stability. All right, so maybe I'll finish here. Thanks.